Reaction rate. Reaction rate is the changes in concentration of reactants or products as a function of time. We have the reactant A to produce the product B. Reaction rate is equal to negative or decrease in the changes of the concentration of reactant A over the time taken, or reaction rate is equal to plus or the production of changes in concentration of product B over the time taken. The unit of reaction rate can be mole per liter per second, or mole per decimeter cube per second, or molar per second. For unit of time, it can be second, minute, hour, day, or year. As reaction proceeds, the concentration of the reactant decreases and the concentration of product increases. The negative sign here indicates the concentration of A, which is the reactant, decreases with the time, while the positive sign here indicates the concentration of B, the product, increases with time. The concentration of reactant and product against time graph. So at the y-axis we have the concentration, at the x-axis time. So the concentration of reactant A decreases over time and the concentration of product B increases over time. Differential rate equation shows the relationship between the rate of disappearance of reactants, because we know that the reactant decrease, so rate of disappearance of reactant, and rate of formation of product, because product increase over time, that's why rate of formation of product. Differential rate equation shows the relationship between both disappearance and formation. For example, we have reactant A plus reactant B to produce product C and product D. So the rate equation, differential rate equation, is equal to -1 over A, small letter a here, 1 over A. This A shows the stoichiometry for the reactant A. Small letter A, stoichiometry reactant A. Small letter B, stoichiometry for reactant B. And the small letter C is the stoichiometry for the product C, and the small letter D is the stoichiometry for product D. So the rate equal to, this is how you write the differential rate equation, rate equal to negative sign because disappearance, the reactant decrease, so negative 1 over stoichiometry of reactant A. Here, if it's 2, you can write 2 here. So D concentration of A over dt equal to -1 over B, here the stoichiometry for reactant B. D concentration of reactant B over dt equal +1 over C. D concentration product C over dt equal +1 over D. D concentration of product D over dt. Example, 1 mole of H2 reacts with 1 mole of I2 to produce 2 mole of HI. So differential rate equation, rate equal to negative sign because this is a reactant, negative DH2. Here is 1 over 1. So we don't show 1 over 1, so it's just negative DH2 over dt equal -1 over 1, because you have 1 here. So 1 over 1 di2 over dt, and equal to positive because HI is a product, so formation of product increase, so positive here, 1 over 2. This is 2 because the stoichiometry of Hi is 2, so 1 over 2 dHi over dt. That's how you write the differential rate equation. Example, hydrogen sulfide burns in oxygen to form sulfur dioxide and water. This is the equation. If sulfur dioxide, the product, is being formed at a rate of 0.30 mole per liter per second, given the value for the reaction rate 0.3, what are the rates of disappearance of hydrogen sulfide H2S? So rate of disappearance, because this is the reactant will decrease, so that's why we call it rate of disappearance. And the rate of disappearance of oxygen, so we have to calculate rate of disappearance for both H2S and O2. First, write down the differential rate equation. Differential rate equation, rate equal to -1 over 2, here 1 over 2 because stoichiometry of H2S is 2, so negative sign because this is reactant rate of disappearance, -1 over 2 dH2S over dt equal -1 over 3. Here 3 is because stoichiometry of oxygen 3, so dO2 dt equal plus SO2. Our SO2 is product, so this is rate of formation. The product concentration increase over time, that's why we use the positive sign here. So 1 over 2, stoichiometry SO2 is 2, positive 1 over 2 dSO2 over dt equal positive 1 over 2, here positive because H2O is the product, so positive sign for the product, rate of formation, 1 over 2 dH2O over dt. So this is a differential rate equation. First, write down the differential rate equation, and then now we have to find the value of rate of disappearance of H2S and oxygen. So this is the rate of disappearance of H2S. This is the rate of disappearance of oxygen. We have the equation, but we need to find the value of rate of disappearance for both. Next, given the rate of formation dSO2 over dt, look at the question again, being formed, SO2 being formed. So this is the product. When this is the product, the rate given is rate of formation. Okay, so here rate of formation dSO2 over dt equal to 0.3 mole per liter per second. This is the value given. So from differential rate equation before here, from here, you know that -1 over 2 dH2S over dt is equal to positive 1 over 2 dSO2 over dt. You compare with the one that you have the value. We have the value for SO2 here, SO2, so compare with H2S and compare that with oxygen as well. So first we compare one by one, dSO2 over dt compare with dH2S over dt. So from there we compare using the differential rate equation, compare for both, the one that we have the value, dSO2 we have the value, so you write down -1 over 2 dH2S over dt equal positive 1 over 2 dSO2 over dt. So from here, just substitute the value of dSO2 over dt because 0.3 is the value of dSO2 over dt. Not this 0.3, not 1 over 2 dSO2 over dt. This value is just for dSO2 over dt. So take this value, substitute into here, it will be 1 over 2 times 0.3. Okay, because in the differential rate equation, the whole thing is 1 over 2 dSO2 over dt. So the 0.3 is dSO2 over dt, not 1 over 2 dSO2 over dt. So just substitute this value into here and it will be 1 over 2, 0.3. And then we have here half dH2S over dt, negative half. So we only need rate of disappearance. We only need this part, dH2S over dt. So you have to remove this half by times by 2. Here times by 2, take this 2 times by 2. And then you get negative dH2S over dt. When here becomes 0.15 and then times by 2, it becomes 0.3 again. And then, so the rate of disappearance, this negative sign is rate of disappearance. So just leave the negative sign here. Rate of disappearance of H2S is 0.3 mole per liter per second. Don't ever put the negative sign at the value. Okay, this negative sign is not for the value, it's just for showing that this is the rate of disappearance. So the value of rate cannot be negative. Next, rate law. Rate law is an equation that relates the rate of reaction to the rate constant and the concentrations of reactants raised to some power. So we have rate of reaction and we have the rate constant and we have the concentration of reactant raised to some power. That is the rate law. It relates all rate constant, concentration of reactants. For example, we have the chemical equation reactant A reacts with reactant B to produce products C and D. So this is the rate law. You relate K with concentration of reactant. Ignore the product. There will be no product at all in rate law. Rate law, we only relate the rate constant K and the concentrations of reactant. No product in the rate law at all. So this is rate law. Rate equal to K, rate constant, times the concentration of A, reactant, to the power M, and times the concentration of reactant B to the power of N. So here M is the order of reaction of the reactant A. N is the order of reaction of the reactant B. So M plus N is the overall order of reaction. In the rate law, you have to put the order of reaction. So rate constant is the proportionality constant for a given reaction and temperature. It does not change as reaction proceeds. This is the rate law. Rate equal K, reactant A to the power of X. This power is the order of reaction for A. This Y is the order of reaction for reactant B. K is the rate constant. For a given reaction, this is given reaction and temperature. It does not change as reaction proceeds. As this reaction proceeds, the value of K does not change. So the reaction order, here X and Y is the reaction order. Exponent of X, reaction order can be 0, 1, 2, 3 half, 3 over 4 and etc. So it can be in fraction. Reaction order can be in fraction. It shows how the rate affected by a reactant concentration. Reaction order shows how the rate affected by a reactant concentration. It cannot be predicted directly from the stoichiometry. So for example, here we have reactant A. So reactant A, the power of reactant A cannot be the stoichiometry of the reactant A in the chemical equation. Cannot be predicted from stoichiometry of the balance equation. How do you determine it? It must be determined experimentally. So don't ever relate the power of the reactant concentration in the rate law with the stoichiometry. It cannot be predicted using the stoichiometry. For example, 1 mole of F2 reacts with 2 mole of ClO2 to produce 2 mole FClO2. Given the rate law K, F2 to the power 1, and here ClO2 to the power 1. If you look at here, this is the rate law. The order for ClO2 is 1, but the stoichiometry is 2. So it's not necessarily to be the same. Okay, for this one, 1 mole, this one order is also 1. So it's just coincident. It's not, you cannot determine it directly from the stoichiometry. It must be determined experimentally. Overall order. Given 2 mole NO reacts with 2 mole H2 to produce 1 mole N2 and 2 mole H2O. Given the rate law, rate equal KNO to the power of 2 and H2 concentration to the power of 1. So for NO reactant, the order is second order. For H2, the order is first order. Here is 1, so first order. The reaction is, you can say that the reaction is second order with respect to NO because the power is 2. So you say it's second order with respect to NO. And here, first order with respect to H2 because the power here is 1. So you say it's first order with respect to H2. And the overall order is the total power that you have in the reactant, for the reactant in the rate law. So 2 plus 1 is 3. So overall reaction order is third order reaction. The overall order reaction can also be determined by the unit of K. If you don't have the power here but you need to determine the order of the reaction, you can also look at the unit of the rate constant K. If the unit of K is mole per liter per second or molar per second, the overall order must be 0 order. If the unit of K is per second, it is first order. If the unit of K is liter per mole per second or per molar per second, it must be second overall reaction order. That's how you determine overall reaction. If you don't have the power here, you can determine the order by looking at the unit of K. Order of reaction unit. Unit K can be determined mathematically for a particular order of reaction. So for example, we know that rate is equal to concentration over time. This is the rate law. Rate equal Ka to the power of 3. So unit of K can be determined if you have the order or the power here. So we know that rate equal concentration over time, and rate law, rate equal K reactant A to the power of 3. So just equal to, for both rate, concentration over time equal to K times reactant A to the power of 3. And put the unit for concentration and time. Concentration is mole per liter, that's a unit for concentration, and the time second. And then we have K, and here concentration, A is reactant, square bracket means the concentration of the reactant. We know that concentration unit is mole per liter. So put the unit, concentration mole per liter, time second, here concentration of A mole per liter, and then K equal to, so you put K equal to, this mole per liter is power to the power of 3, so you can calculate K equal mole negative 2 liter power of 2 per second. So this is the unit K. This is the unit K. When you know that this is third order, so this is the unit K. That's how you determine the unit of rate constant. Half-life. Half-life is the time required for the concentration of a reactant to decrease to half of its initial concentration. So initially you have 100%. The time taken for this amount to become 50%, you call it half-life. That's the first half-life. For the initial amount to become half, the time taken is the half-life. And then now you have 50%. Half of 50% is the second half-life. So half of 50, 25%. And then half of 25% is about 12%. That's the third half-life. And half of the 12 is 6%. That's the fourth half-life. And half of the 6% is 3%. That's the fifth half-life. So half-life is the time taken or time required for the concentration of the amount to become half of its initial concentration. That is half-life. We look at the time.